over something that we already had an answer for, just to show you how this works. Let me try to rederive the product rule using logarithms. Suppose u and v are differentiable functions of x, and I want to find the derivative of u times v with respect to x. In other words, I'd like to find dy dx. Okay, I take the natural log of both sides. In other words, I say if y equals u times v, then natural log y equals natural log u times v. Okay? Now, what is the property that the natural log function has? I deliberately chose it to be that member of the L family that was logarithmic. The natural log of u times v is natural log u plus natural log v. Now, can I differentiate this implicitly with respect to x? You see how all of our old stuff keeps coming up in new contexts. I take this equation and I differentiate it implicitly with respect to x. The derivative of the left-hand side is 1 over y dy dx. The derivative of the right-hand side is what? Well, the derivative of log u with respect to u is 1 over u, but I'm differentiating with respect to x, so I must use the correction factor by the chain rule, du dx. And similarly, the derivative of log v with respect to x is 1 over v dv dx. And now multiplying through by y, I have obtained that dy dx is y over u du dx plus y over v dv dx. But remembering that y is equal to u times v, this becomes v du dx plus u dv dx. And we have arrived at the familiar product rule using logarithmic differentiation. You see, the point that's really important to stress here is that it wasn't important whether the natural log was an exponent or not. The important thing that we used about logarithms, whether it was our high school course, whether it's going to be in our college calculus course, the important thing was what? That when we wanted to write the log of a product, it was the sum of the logs. And now the only additional fact that we have from the calculus approach is that the derivative of log x with respect to x was defined to be